Hi, hi to everybody. In this lecture video, we are going to be dealing with radiation. And the specific goal after doing this chapter, you will be in a position to be able to explain what is the radiation, and you'll also be able to derive the electric and magnetic fields of oscillating electric and magnetic dipole radiation. And you will understand the concept of the radiation from arbitrary sources, and you will also be able to derive the Gamma formula, and you will also be expected to solve the problems on the above concepts. Now let us just start with dipole radiation. Now from the previous chapter, we know what is the retarded potential. The retarded potential are given by this equation where you have the scalar potential and you have also a vector potential, and this R in this equation is nothing else but the separation vector from the field point to the source point, and the TR is nothing else but is the retarded time. Now the idea is always you have to know the potentials, because after knowing the potential you can be able to determine the both fields, which is electric field and magnetic field, because E is actually given by negative gradient of the scalar potential minus the time derivative of the vector potential. So now if you know the potential, therefore you can be able to tell what are the fields, where B, the magnetic field, is nothing else but it's just the curl of a scalar vector potential A. So that's the idea. You first determine what are the potentials, and then from there you can easily be able to determine what are the fields. Yes. Now after knowing the potential, therefore one can be able to determine what are the fields, and these were given by Jeffremenko's equation, and the fields were just given by these two equations for electric field and the magnetic field. Right. So now the radiation is electromagnetic energy that travels out from localized region and never to return back. Now, although both fields extends to infinity, but not all of their parts contributes to radiation. For an example, the parts with one that varies with 1 over r do not take part or contribute to the radiation. For an example, this part and that part, as you will see a little bit shortly. Now, the rate at which electromagnetic energy flows through an area dA is given by the S dot dA, where the Poynting vector is E cross B. Right. If you consider a huge imaginary sphere of radius r surrounding a region where fields are produced, then the rate of energy flow, or the power, is just given by the surface integral of S dot dA, and this, because we know what is S, can be written by this equation, using this equation here. Right. Now, as the radius r of the sphere increases, the size of dA, the surface area of that sphere, also increases with r squared. So if E cross B decreases, this will decrease because E and B are inversely proportional to r squared. Therefore, this will decrease faster because of 1 over r squared, Then in the limit, as r goes to infinity, the radiation is therefore 0. Right. Now, therefore, the radiation, as I've said, is associated with the electric field and magnetic fields parts that varies with 1 over r. Therefore, the contribution of the electric field from the contribution for the radiation is only for these terms, for electric fields and the magnetic fields. Therefore, this term is always being neglected for the contribution to the electric field, because it will decay fast, or it will just vanish quickly because of 1 over r squared. Therefore, we will be considering the specific case of an oscillating electric dipole and an oscillating magnetic dipole before considering the general case. All right. Now let us just start with oscillating electric dipole. Now consider a charge flowing between two small spheres with negligible radius at position both placed in z direction at the distance d, joined by a thin wire. Now in that case, the top sphere is just given, the top charge has the Q magnitude of this Q naught cos omega, while the bottom one will just have a negative here because the charge there is negative. Now together, the net charge is 0 and the system is an oscillating dipole. With dipole moment is just Q multiplied by D, but they are in Z direction, and that is in Z direction. But we know what is Q from there. The Q is just given by this, and this is just going to be given by this, where P naught is nothing else but this Q naught times D. Now, under the condition where we are trying to make this physical dipole a perfect dipole, and that the condition there will be D is much greater than R, it's much less than R, or is much less than C over omega, or is much less than lambda divided by 2 pi. And if we define alpha to be omega times T minus R over C, the fields are therefore given by the following equation. Now the electric field will be in theta, but look, it's got a negative sign there, and the magnetic field, it will be in phi direction, and also it's got a negative sign there. Now if we know the both fields, therefore we can be able to tell what is the Poynting vector. Right, now these fields are perpendicular to each other. For an example, the ratio of E and B is just given by this equation here. They represent the spherical wave with have an amplitude decreasing like 1 over R as they propagate outwards. The corresponding Poynting vector is therefore E cross B. Now if I have in spherical coordinates, I have R, I have theta, I have phi there. Now if the electric field is in theta and B is in phi, therefore theta cross phi is in R. As a result, that's why you are seeing the Poynting vector is always in R direction, or in unit vector R. So this is what you are going to have for this. But we know that the time average cos squared alpha is just half, and it means that this can just be given by this equation, because this is just half. Right, now the sine theta distribution has the pattern of a tornado or donut, but without a hole at the center. Now there is no radiation in the direction of the dipole moment, and maximum radiation occurs perpendicular to this xy plane. What does that mean, by the way? I just want to remind you the sine theta. Now the sine graph is just given by this simple graph. As you always remember, the sine graph is given by this graph, where here is 2 pi, and there you have pi, and here you have pi half, and there you have pi 3 pi halves. Now as this statement is saying, when you have the anti-parallel and then the parallel vectors for the velocity as well as the acceleration, therefore there you are not going to have any radiation. But the radiation, the maximum radiation, you are only going to have it when these are perpendicular to each other. Right, so that's what this term is saying, the sine squared term in that equation. Therefore, radiation occurs perpendicular to xy plane. Now the total time average power radiated is just therefore given by this equation, the average S dot dA, the average Poynting vector dot dA. Now if you plug the answers for that we have received for that, and the dA is nothing else but this R squared sine theta in spherical coordinates. Therefore this is what you are going to have. And maybe I should just show you how to move from here to there. Now let's consider the fact that if you have the integral, I just want to start with the fact that when you have a theta when you have a theta, in spherical coordinate, theta will always be going from 0 to pi, but phi will always be moving from 0 to 2 pi. I hope you still remember this from the previous lectures, especially the first semester one. Now in here, if you have 0 to 2 pi, and then here you have d phi, so this is obviously going to be 2 pi. So the first part, this part, of the integral d phi is 2 pi. As you can see, it's just 2 pi. But let us also do the integral from 0 to pi, and then you have the sine theta d theta. Now this can also be written as 0 to pi, and then this is sine squared theta times sine theta d theta. Now I can also write that in terms of the integral, but I am just going to leave the integration limits for now. I can write that as 1 minus cos squared theta, and then there must be a sine theta d theta. And when I'm there, I'm just going to let u is equals to the cos theta, and therefore du is just going to be minus sine theta d theta. Now if I go back and then plug this u in there, I will just have the integral of 1 minus u squared sine theta d theta. It must be minus du here. Now if you take out the integration, you are just going to have minus u plus u cubed divided by 3. Now from there, you can just write this to be that, and now here you are just going to have this can be equals to u is minus cos theta plus cos cube theta divided by 3, and this must be from 0 to pi. Now if you do that, what are you going to have? You are just going to have this is equals to minus the cos of pi plus cos cube of pi divided by 3 minus cos of 0 plus cos cube 0 divided by 3. Now after solving this equation there, you can eventually be able to show that this is nothing else but this is 4 over 3. Right. Now in this chapter, whenever I see something like this, the integral of this, I'm just going to write 4 over 3 to pi. Right. So that's what I wanted to show you. Right. Now, to obtain the fields of the oscillating electric dipole, in order for us to be able to determine the fields, of course, we just have to determine what is the potentials. Therefore, we have to determine the potential first. So now, in this diagram, as you can see, that the distance from the positive charge to the point to the field point where we will be measuring is given by R plus, and from the negative charge is given by R minus. Now, if this angle here is theta, therefore this angle here will be 180 minus theta. Now if we are going to be using the cos rule, as you can see, this will be minus cos. It will be minus cos. Right, now the scalar potential is given by this equation, and of course this is the integral. If we take the integral, the top one is the positive charge, the charge density, plus the bottom one, so that this can just be written in terms of the point charge Q, and then here you have the TR, and then R plus, and then here you have plus, but here you have minus because this Q is negative. This charge here is negative. And then from there, we know what is Q. Q is Q naught cos omega alpha. So this is what you are going to have for this equation, where R plus is totally different from R minus, because R plus is this distance, and then the R minus is that one. Now, if you use the cosine rule, if I have to remind you, if you have a triangle like this, say you have a triangle of this nature, and then say here you have A, and then here you have B, and then here you have C. Now, if these small angles here, if this angle here is small c, and then that angle here is small b, and that angle here is small a, Now, the cos rule tells us that c squared is equals to a squared this side is equals to the a squared plus b squared minus 2ab, the cosine of c. So we are just going to use this equation, which is the cos rule. Now, in that diagram, so now if you use that in this diagram, what are you going to have for say R plus? For R plus, you are just going to have the R square, and then R square in this triangle here. You are just going to have this equation here. But in this triangle here for R minus, what are you going to have? You are just going to have R square plus d divided by 2 square minus 2R d divided by 2, but the cosine of 180 minus theta, because this angle here would be 180 minus theta. Now, the cos of that is just going to be minus. Therefore, that minus, when it multiplies with that minus, just going to give you positive. Right. So that's what I want you to see. But what we really want is not the R squared. We want 1 over R plus or R minus. Therefore, so that we can just plug things back there. But before we can actually do that, we just want to make this physical dipole a perfect dipole, and that is for this condition where d is much smaller than r, and that is just going to be given by this equation, because this term here will just die because r is much greater than d. So therefore you will have this equation, and that equation can actually be simplified to these equations that you are actually seeing there. Right. Now, after doing that, we want to use this expansion, because we have the cos of v and minus u there. Therefore, we want to use this expansion in order to write that. Now, and also we want to take that omega over, times d divided by c is much smaller than 1 with small angle trigonometry formula. The small angle trigonometry formula, remember, is just given by, for an example, the sine of a very small angle, theta, is approximately equals to theta, but the cosine of a very small angle is just equals to 1, and the tangent of a very small angle is just equals to theta. Is approximately equals to theta. So I hope you still remember those conditions. So those are the conditions that we are going to be using. Now, I want to write this in terms of this expansion. Now, if I want to write this in terms of this expansion, because here I know what is r plus or minus, is just given by this equation here. Now, I want to write this, and then I am defining alpha. I've defined alpha to be alpha is just given by omega t minus r over c, and then here you have omega. So that's your alpha, the definition of alpha. Right. In that case, therefore, I can just write alpha. Instead of writing omega r over c, I can just write alpha, and this will be that times that will just be given by by this equation when we use this small this conditions that we have put, because omega d divided by c is just smaller than 1, therefore that term will just be ignored there. Now if I use that to expand this, I will just write it in this fashion. So this is what I'm going to write. But now when I'm using the small angle approximation, for an example, the cos of a very small angle is just 1, therefore that's why you are just going to have a cos alpha. But here you have the sine of alpha. The sine of alpha is there, but the sine of a very small angle is just equal to that angle. This is what you are seeing there. Right, now from there we also want to simplify that equation of r plus or minus to be 1 over r plus or minus, so that it can give this. And now if we are having this gives us the potentials to be like this. We just combine this to the equation of the potential, therefore this is what you are going to have as the potential. And this can also simplify further, because if you multiply out from the first 4 terms, 2 terms get doubled and 2 cancels, and this will yield this. For an example, the cos alpha term will cancel with this 1 multiplied by 1. If we take 1 over r as a factor, cos alpha multiplied by 1 will cancel with minus cos alpha multiplied by 1. But this one is got negative here, multiplied by this, and it's got negative, and it's also got negative there. Therefore, that multiplied by that will just be adding, because you have minus, you have this multiplied by that, and then it's minus multiplied by minus. Therefore, it will just be adding. As a result, this is what you are going to have, and you can simplify this further to have this equation here. Right, you can simplify that further, because if you have, since you have c over omega is much less than r, the first term will just vanish. Now I just want to write this condition here so that I can just explain this. Now we are putting this condition, c over omega is much smaller than r. We are making that physical dipole to be a perfect dipole, and this is the condition. Now if I want to write omega over c, that is just going to be much bigger than r. So now as a result, in these two terms here, the term that is going to die is not this one, because omega here is the numerator and omega there is the denominator. Therefore the term that is going to die is this one. So as a result, this is what you are going to be left with. So I always want to show you that you need to be very careful of this c over omega and omega over c. So this is what you are going to have for your potential. Now after knowing the scalar potential, therefore I can be able to determine what is the vector potential. Vector potential is just given by this equation, but the current upwards along a line is just given by, if you know q, if I know q was just given as q naught, the cosine of omega t. So as a result, in this case, if I want the current, I will take the time derivative of q. Now this is just going to give me q naught, and then I have the sine omega t, and then do the chain rule, I will have omega here, and there must be a minus, because when you differentiate cos, you have minus cos. So this is what you are going to have. So this is omega. So that is omega. There must be omega here, and then the minus there. So that's what you are seeing in that equation here, because now I'm know the q, and then I can differentiate that with respect to time, and then I can actually replace that for a line, not the volume current. Then I can write I here, therefore I can have this in terms of this. But it is also important, we can replace the integrand by its value in the middle of the interval where d is equal to 0, because we are trying to make that physical dipole to be a perfect dipole. D is equal to 0. That is the perfect a dipole. So R is equal to R. Whenever I see the big R, I'm going to write the small r. Now, which gives us this equation here. Now, this is just going to be given by this. When I have defined I write this sign of alpha because I've defined alpha to be this. So now that is just going to be given by this. But I want to write the unit vector in terms of this. So this is what I'm going to have for A. Now I know the A, I know the V, therefore I can be able to tell what are the electric field and the magnetic field. Now in spherical coordinates, the gradient of a vector is given by this. Now from that, you can just be able to see that I'm going to differentiate this with respect to R in R unit, and then this term here is outside the differentiation of V, and this term here is outside and phi, but the phi is going to be 0 because the potential doesn't depend on phi. Now in this case, for the example, let us just do the first term. If we do the first term, we are just going to use the product rule there, and the product rule, as you still remember, the product rule is I'm going to differentiate f, and then I leave g, and then I add g prime, and then I leave f. So this is what I'm going to do with this. So for an example, I can call this one here, I can call it f, I can call it f, and then I can call this one g. Now I'm going to leave this and differentiate this. When I differentiate this is just going to be r minus 1, and then that will be minus r squared, and when I take it down, it's just going to give me this. So this is what I'm going to have this. Now this time around, I'm leaving this, and then I'm differentiating this. When I differentiate sign, I'm going to have minus cos. So this is what I'm going, but that is in R. And then you also do the same for this part. That part is just going to give us 0. Now after doing that, this is what you are going to have. And what is very important here is the fact that this gradient of V will just be in unit vector R, in R direction. Right. So now I also, yes, this R will always be cancelling from each other. This term there will cancel because they vary with 1 over r squared, and those varying with 1 over r squared, they don't contribute to the radiation. Therefore, this will just cancel each other. So, and this one is because this scalar potential doesn't depend on phi. As a result, this is the final equation that you are going to have for the gradient. Now, we are in a position to determine what is the electric field. Now, we are just going to add this term here because we have it here. And then when we differentiate this with respect to omega, we are going to have the same thing, but here you are just going to have the cos and then omega, and then you are going to have omega because we differentiate with respect to t. So this is what you are going to have. And here, those ones in R unit vector will just cancel each other. Now, after cancelling each other, therefore, you are just going to have your electric field as given by this equation here. Right. Now, the magnetic field in spherical coordinates, we know what is the curl. The curl of a certain vector is just given by this. But what is very interesting here is A doesn't depend doesn't have anything in unit vector phi. What I'm trying to say here is A phi is just equal to 0 because A doesn't depend on the unit vector, but it depends on the R, and then it also depends on theta, but there's no phi. So that's what I'm trying to say, and that makes this differentiation very simple because all these terms will just be 0, but we are just going to be differentiating with respect to this unit vector phi, and then A that is just equal to 0 because the A doesn't depend on phi. As a result, this is just going to be 0, and therefore the term that we are going to consider is this one here. and taking into account that this is outside of the differentiation, and now you have to take the differentiation. If you take the differentiation of that, this is what you are going to have. You differentiate with respect to r, and this is what you are going to have, and this one you are also going to have this. Now the final equation there is just given by this, and this term here, which varies with 1 over r, will also not take part into the final radiation. Therefore it can be ignored. As a result, the magnetic field will just be given by this equation here. Right, now because we know E and B, therefore we can be able to tell what is the pointing vector for this. We can also be able to determine what is the pointing vector, because in that case you are just going to have the pointing vector is just given as 1 over mu naught E cross B. And if E is in this case the electric field is in theta, and then the magnetic field is in phi. Theta cross phi is always in r. Therefore the electric field will be in unit vector r. That will be in unit vector r. Yes, so that's your pointing vector. But now let us also consider the oscillating magnetic dipole. Now consider an alternating current given by this flowing around the loop. This current is flowing around the loop of radius b around the origin in the xy plane. So now in this case the system is an oscillating magnetic dipole with the magnetic dipole moment given by this equation, where I naught pi b squared is just given by m naught. Right, so this is what you are going to have. Now, under the condition where this b, the radius is much smaller than the r, is much smaller than the r, and define alpha to be this. Therefore, it can be shown that the electric field is just given by this equation, and the magnetic field is given by this equation, and this is what we are going to be proving. But as you know, that the ratio between E and B, and E and B are always perpendicular to each other, and the ratio is just given by the speed of c. And this, they represent the spherical wave with have the amplitude decreasing as 1 over r. The amplitude will be decreasing as 1 over r as they propagate outwards. Now the corresponding pointing vector is therefore given by this equation here, because we have you have the electric fields in phi, but the B is in minus theta. Therefore, phi cross minus theta, it is always in R. What I'm trying to say here, maybe I need to write it down. If in spherical coordinate I have R, and then I have theta, and then I have phi. Now, if I have minus phi, therefore theta, or the phi cross minus theta is in R. Yes, is in R. But phi cross theta is in minus R. Phi electric field, phi cross minus theta, it is in R. So that's what you are seeing in that equation. What I'm trying to say is, you need to be careful that this is in minus theta direction. It is in minus theta direction. Therefore, phi cross minus theta direction is in R. So that's what you are going to have for your S. Now, because we can also find the time average, because the cosine squared alpha is just half. Therefore, the time average pointing vector is just going to be given by this equation. Now, this is very important because the sine square distribution has the pattern of a toroid or donut, but without a hole at the center. Now, I also want to remind you that there is no radiation in the direction of the dipole. This is because of this term, sine squared. In the direction of the dipole, there is no radiation, and the maximum radiation occurs perpendicular to xy plane. Why is this the case? For an example, we can just simply define this as, for an example, this graph of sine theta is just simple as this. So this is the graph of sine theta. look at when this is anti-parallel, when the acceleration and the velocity are anti-parallel, therefore this is just 0. But the maximum here of this graph we are just going to get when this thing is 90 degree, or they are perpendicular to each other. And then of course here is you have 360 here, and then you have 270, you have 180, and then you have 0 there. So this is what it is saying, if you still remember what is the sine graph. Right, now the total time average power radiated is therefore given by this equation here, and of course whenever you see that, you just write this. So this is what you are going to have as an total time average power radiated. Now the ratio between the total time average power radiated from the magnetic to electric is just given by this equation, which is generally small, so that the electric dipole radiation is more effective than the magnetic dipole radiation. Right, now in order for us to obtain the fields of an oscillating magnetic dipole, we first calculate the potential. After knowing the potential, of course, we can be able to determine both electric and magnetic fields. Now the scalar potential is given by this. This is just equal to 0. Since there's no charge density, you only have a current that is actually moving around that loop. Therefore, you don't have any charge density there as a result. Therefore, this is just going to be given by 0. But the vector potential is just given by this equation or for a line current. For a line current, we have to substitute J with I. And then this is what you are going to have. And we know what is I. I is just given by I naught cosine of this angle, and where the direction of the current has been transferred to the circuit element. Now in this case, suppose a point of interest that the R where we want to measure is above the x-axis as shown in this diagram. For two sections of the current loop at plus or minus phi, the values of R will be the same, while the x component of dl will be equal but opposite and cancel out. Now in that case, this leaves us with the A vector in y direction. The A vector will be in y direction, and then we are moving from 0 to 2 pi for phi, and that dl can just be written as b cos phi d phi. Now if you use the cosine, because we want to know what is r, 1 over r, but we can be able to determine what is r squared first. You use the cos formula, and this is what we are going to have, and we want to write this rb as r dot b. So this is what you are going to have, but we need to determine what is this vector r, what is this vector r, and what is this b, vector b. Now if you plug the definition of the vector r, because vector r is defined by this and the vector b is defined by this, and you plug back to that equation here what is vector r and dot b, and only the ones that are going to take part is this one in the x component, the one in the x component, that one and that one will just vanish, because we are taking the dot product of r dot b. Therefore this ones, therefore will just give you this equation over here. But still we want to have 1 over r so that we can plug back these things into the equation, but we consider the conditions where b is much greater than, or much less than, r, and this is what you are going to have, because this term here will die because it's much smaller than r. It's not going to have any effect. Therefore we are going to kill this term there, and then you are going to end up with this equation here. Now what we want to do is to simplify this r a little bit further. Therefore r will just be given by this equation, and of course we just use the same expansion for the cos, because on that equation we have this something like that. And now as you have seen previously, and then you use the small angle approximation, this is what you are going to have. Now with this we are ready to write this in terms of, or maybe we need to simplify r to be 1 over r. Now in that case, if you simplify that, this is what you are going to have. Now we are ready to write the vector potential, which is nothing else but that multiplied by that and some other terms which were there. So this is what you are going to have for your vector potential. Right, now you can even simplify it further, and this is what you are going to have, where in the final answer, the terms with b squared have been neglected. The terms with b squared have been neglected because this is much smaller than 1. The terms with b squared, that multiplied by that, have been ignored in this equation. That's why you have this and then these other terms, but that one and that one have been ignored because of the conditions that we have placed there. Right. Now, the first term in this equation here, if you differentiate that with respect to that, that is just going to give us 0, because we are integrating around the loop. We are integrating around the loop. So this is what you are going to have, because the cos of 0 is just the same as the cos of pi. Now maybe I must just remind you the cos graph is something like this, is drawn like this. The cos of 0 and the cos of that is just the same, because it's just 1, because here you have 2 pi and there you have pi. So the cos of 0 and the cos of 0 and the cos of 2 pi are just the same as 1, but you have minus. Remember, when you take the upper boundary of the integration and you minus the lower, therefore you are just going to have 0 for that one, and then you will have this. But when you take this into account, and I'm just going to explain it for the last time, if we are saying c over omega, c over omega is much less than r. Now, if you want to have omega over c, that changes to be that, will just be greater than r. Now, as a result, that will be greater than r, therefore this term will die. You need to be careful, this term will just vanish, and now when this term vanishes, you will just be left with that term. So that's what I am trying to show you there, and that was for the last time. Now, this equation will just be given by this equation here. But we know what is the cos squared. The cos squared is nothing else but it's half, but the integral of the cos is nothing else but it's just the 2 pi. The integral of the integral d phi is nothing else but it's 2 pi, and then when you multiply, you are going to have pi. And now if you simplify the equation further, this is what you are going to have for your vector potential A. And also, if we know that if the point of interest did not lie on the x-axis, then in general the vector potential A will lie in the phi direction, so that in general we have this as your equation. Now we know the potential, and we know all the potential, therefore we can be able to determine what is the electric field and the magnetic field. Now the electric field will just be determined in terms of this. Now you take the time derivative of this. Now if you take the time derivative of this, this is going to be cos, and then you are just also going to have the omega there. So that's why you have the omega squared, because this comes with its omega. But now if you differentiate this, you are going to have an omega, therefore that's why it's omega squared there. So that's your electric field. Now after determining the electric field, we also want to get what is the magnetic field. And in spherical coordinates, the curl of a certain vector is just given by this. Now, knowing that a theta and AR are just 0, because this vector potential A is only in phi. Therefore, E theta and ER are equal to 0. It makes things to be simple. And now this equation, we are only going to consider AR is just equal to 0 and A theta is equal to 0. Therefore, these terms, 4 terms, will just be equal to 0. This term and that term and that term and that term. The only terms that we are only going to have is this one and that one. Now, if you do that, if you do the differentiation with respect to theta, and remember this is outside the differentiation and this is outside the differentiation, so this is what you are going to have. And remember that this is in unit vector in r direction, and this is in theta direction. This is in theta direction, which means in phi I have nothing because of this. AR is equal to 0 and A theta is equal to 0. Now after doing this differentiation, this is what you are going to have to for the magnetic field, which can also be simplified to be written in terms, because the sine squared can be written in terms of this. So now neglecting the first term, which varies with 1 over r, this is just going to die. Therefore, we are just going to have this as your magnetic field. Now, let us also consider the radiation from the arbitrary source. For an arbitrary source, under the condition that one is far from the source, one only considers the terms of the electric and magnetic fields that varies with, which are proportional to 1 over r. To contribute to the radiation, one can show that the fields are given by this and that. Now, where P is the dipole moment of the source producing the radiation, and P double dot vector is to be evaluated at the retarded time. Now, because we know E and B, therefore we can be able to tell what is the pointing vector. But it is easier to continue by assuming that P is in Z direction, P double dot is in D, so that the R cross P is in P, because the cross product of two vectors, remember, if you have A cross B, if you have A cross B, this can be determined in terms of the magnitude of A and magnitude of B, the sign of an angle between them. So that's what I am going to be using. Now, in that case, the R cross P there is the magnitude of the unit vector is 1, and then the magnitude of the P double dot, not the vector anymore. Therefore, this is the sign of an angle, and it is in minus phi. And therefore, if that is in minus phi, the unit vector R cross minus phi will just be in theta. Will just be in theta. What I'm trying to say here is, if you have in spherical R theta and phi, if this is in minus, R cross P is in minus theta, is in minus phi, therefore R cross minus phi is in theta. R cross minus phi is in theta, but phi cross R is in theta. R cross minus phi, it is always in positive theta direction. Right. So this is what you are going to have for your electric field, because we know what is that. That is given by that, and it is in theta, and the magnetic field is actually in phi. Now, in order for us to determine the Poynting vector, is just going to be given by this theta cross phi. Theta cross phi is in R. Therefore, that's why you are going to have your Poynting vector as in R. Now, we can be able to determine what is the total power radiated. The total power radiated, the moment you see this, as we have done previously, you can have this as your total power radiated. For an example, suppose that this is the dipole moment is given by this equation here. Now, if you differentiate this twice, you are just going to have minus P naught omega squared, because you differentiate this with respect to time twice. This is what you are going to have. Now, we can just plug and evaluating this at T naught is equal to T minus R over C. Therefore, this is just going to be equal to this, because this is just this part, which is a constant, but now P double dot is this, because we know that you just have to square that. Now, if you want to write this in terms of that, this is what you are going to have, and this is nothing else but this is just the same as mu naught. This is just the same as mu naught. This is just the same as P is equals to mu naught P naught squared omega to the power 4. This must be divided by 12 pi C, which is just the same as what we have actually previously calculated or obtained for the oscillating electric dipole. Right. Now, to obtain the fields of an oscillating magnetic dipole, we first calculate the potential. Now, fields near oscillating magnetic point, we just have to know the potentials. Now, the potential is given by this, and now the cosine rule, if you use the cosine rule, this is what you are going to have for the cosine rule. So this is what you are going to have for the cosine rule. Now, we can simplify these equations to be like this. So now, in order for me to have this here, I'm just going to take this term here. I'm just going to take the last term there, and the last term there is nothing else but it's just this multiplied by that is R. That multiplied by that is just going to give me R r vector dot the source, and then that will be divided by r squared. And now I want to write a very important definition of the unit vector here, which we will always be using. The unit vector is just given by the vector divided by the magnitude of r. Now if I want to write the r vector there, the r vector will just be given as the unit vector times r. Now whenever I see the vector r, this is what I'm going to write. Now in this equation here, I'm just going to have r, this is just going to be, I'm just talking about this, I'm just doing this last part here. I'm just doing this last part here. Now whenever I see the unit vector, this is just going to be r vector, I'm just going to have, and then I can write square here because that would be that other r, but that must be dot with the source, and then here I have r squared. Now this r will cancel, this r will cancel, and then I will end up with unit vector r dot. So that is this part here, because this is what I am just using. This is this part here. So as you can see, this is what you are going to have for that. Now for r, source is much less than the field point. Therefore, this is what you are going to have. This is what you are going to have, because the other term there will just vanish, or this other term here will vanish, and then that's what you are going to have for this. Now the charge density at the retarded time can therefore be expressed as this. Now we know what is TR is given by this, but we know what is R is just given by this, and now if you plug that R there, this is what you are going to have. Now the charge density will just be given by this, where T naught represents the retarded time relative to the origin. Now this can be expanded via a Taylor series, and then the charge density can just be written like this final term there. Right. Now we must also find what is 1 over r, because we want to go back to the potential so that we can plug things back, because we know what is the charge density. It can be plugged there, but we want to know what is 1 over r. 1 over r. 1 over r is just given by this. Now the potential can just be this constant times that and that. So that will be your potential. Your potential will just be this, because we know what is the charge density. Charge density is given by that, and that is just that. Now this equation can be written in terms of this, where the final term that involve the r squared has been neglected, because the r prime is much less than the r. So as a result, that term will just be neglected. Now this can be rearranged as follows, because we know what is the integral rho d tau is nothing else but is the total charge. Now this can be written in terms of this equation, where the dipole moment is just given by this, is the dipole moment that. Now the first term to corresponds to the fixed point charge, which is q, which does not result in the radiation, because the radiation will only be a result of the moving point charges. For the third term, which varies with 1 over r, therefore, and this does not result in the radiation, because it will decay quick. The potential will decay with 1 over r squared. Now therefore the potential is just given by this equation here. Now the vector potential is just given by this. This is a vector potential, but now this can be, for r is proportionally equals to r is sufficient. Therefore whenever I see r, I'm just going to write small r. So this is what you are going to have for the potential. But now I want to write J as the charge density multiplied by V. If you do that, this is what you are going to have for this equation. The time derivative of the PR is nothing else but is P dot vector. Right. So that's what you are going to have. Now you know the potentials, therefore you can be able to determine what is the fields. The electric field will therefore be given by this. And now if you use the chain rule on the first part, this is what we are going to have, because the time derivative here will have the double dot here of your P. Now if you use the chain rule in there, this is what you are going to have. But if T naught is define as this, and then this is equals to 1, and this is just given by minus r, because you have to differentiate this with respect to r. That will be the negative in the unit vector r divided by c, because this is a constant. You are not going to be differentiating that because it doesn't depend on r, but this is just going to be this. So now if we plug these values in this equation, so this is what we are going to have, and this can be simplified to this, and of course this can be written in terms of this, but this can also be written in terms of the backup rule. The backup rule, which is nothing else but is the, if you have the A cross B cross C, is nothing else but is just backup So now if you use that in that equation, you can easily show that this can be written in terms of this triple vector product. So that will be your electric field. Now what will be your magnetic field? The magnetic field will just be a curl of this. Now if you, because you know what is the vector potential A is just that. Now if you change the variables in that case and use the chain rule, you are just going to obtain this equation here. We are just going to obtain this equation there. So now let us also talk about the radiation for a point charge. For a moving point charge, the linear Wishart potentials are given by these two equations. Those are the potential, the scalar and the vector potentials. Now from these equations, as you know, with the potential, therefore we can be able to determine what are the fields. The fields were calculated to be this for both the electric and magnetic field, where U is nothing else but just given by this equation here, and that from the backup rule, therefore we can write this in terms of that. Now therefore radiation is the electromagnetic energy that travels out from the localized region and never to return back. Yes, never to return back, and not some of the electric field and the magnetic field will contribute to radiation, but the one that varies with 1 over r squared is not going to contribute anything to the electric field. Now the rate at which energy flows, which is nothing else but is the power, is just given by S dot dA, where S is just given by a Poynting vector, which is E cross B. Now the power is just given by this equation. This is what you are going to have for your the power radiated. Now as the radius r of the sphere increases, the size of dA in spherical quantity will always increase with r squared. So any part of the Poynting vector which decreases faster with 1 over r does not contribute to the radiation, since we work in the limit where r goes to infinity. Now consider the specifically a point charge for which the electric field is just given by this and the magnetic field is given by this equation. Now then the Poynting vector is just given by this. This is just going to be your Poynting vector, and when you use the backup rule, this is what you are going to have. Now since the electric field is a square in both terms, any part of it that decreases with 1, that decreases faster than 1 over r, do not contribute to the radiation. Now as a result, the total electric field of the moving point charge is just given by this equation there. Now but the first term in the square brackets, does not contribute to because this decays with 1 over r squared. Therefore this leaves us with the electric field related to the radiation to be given by this equation. Now since this is perpendicular to r, since that electric field is perpendicular to r, the second term in the Poynting vector, the second term in the Poynting vector, the second term in the Poynting vector falls out, and the corresponding radiation is just given by this in the Poynting vector, this term here. would just fall to 0. Why that is the case? Because R is perpendicular to, remember, you have E dot R in this term here. Now, what are we saying is, if we have A dot B, this is just the magnitude of A, magnitude of B, the cosine of an angle between them. Now, what is the cos of, but in this case, this can be written as E dot unit vector R, and that will just be E, the magnitude of E, the magnitude of unit vector R, and then the cosine of an angle of 90 degree. Now, if you plot the cosine of 90 degree, so this is what you are going to have, the cosine of 90 degrees. So this is what you are going to have. That is going to be 0. As a result, that term will fall. That term, the second term in here, will just fall, because that is perpendicular to, this is perpendicular to that. So you will end up with this equation as your Poynting vector related to the radiation. Now, before considering the radiation, the radiated power in general, we consider a simple case when the charge is at rest, V is equal to 0, and the acceleration is not. Now, in this case, if V is equal to 0, this term will cancel, and you are going to have this. Now, from that equation here, this is what you are going to have. This is what you are going to have, CR. Whenever you see U, you are going to have CR. So now you can write that in terms of this, and this is what you are going to have for the electric field related to the radiation, and therefore the Poynting vector corresponding to or related to the radiation or contributing to the radiation is just going to be given by this equation here. And I want you to see that this is just the same thing. And now this is 2, therefore you just have 1 there, because it's A dot R. It can be written as magnitude of A and magnitude of R. Magnitude of R is just 1, the cosine of an angle between them. So this is what you are going to have. Now, this is what you are going to have, and we still have that sine squared theta term in that case, which tells us that where theta is an angle between the acceleration and the unit vector R. Now, as a result, this factor means that there is no radiation parallel or anti-parallel to the direction of the acceleration. What does that mean? Because if you plot the sine graph, the sine graph is like that. Therefore, here is parallel and anti-parallel. Therefore, as you can see, that there's no radiation, because the sine of theta there is just equals to 0. And then the maximum, of course, is just only going to be for the perpendicular to the acceleration. When the unit vector is perpendicular to the acceleration, therefore you will get the maximum. Now, the total power radiated is just given by this, but now we know we have solved this. We know what is that. This is just given by that, and therefore this is just given by this equation. And that is the Lauma formula, which predicts that the radiation is proportional to A squared. The radiation is proportional. The power radiated by radiation is proportional to A squared, although we derive it from the special case of V is equal to 0. It is a good approximation for non-relativistic moving point charges, where V is much less than C. Now, the next is to consider the radiation power in general, and in this case we cannot simplify this. We cannot predict that V is equal to 0. Therefore, we just have to write it as it is there. Now, if you write it as it is, this is what you are going to have for your Poynting vector. So, right, now, in addition to this more complex formula, there is an even more important complication, because now if we have to get the power is SR dot dA, represent the rate of energy flow, part the large sphere around the point charge at the present time. Now, the power is just given by this. Now, I just want to show you something here and then write it very nicely, that the power is just given by over. Now, I want to multiply that by dt. I'm just multiplying it by 1. There's nothing that I've done there. Now, this can be written in terms of dt, and then here I have dtr. Now, if I want to write divide there, this is just going to be d over dt, and then if I write divide there, that will switch dtr over dt. So that's what I'm going to have, and that is what you are actually seeing in this equation here. Now, we already know what is this. If you can look at your previous lecture slide, this is just given by that, so that I can just write this whenever I see that. And then this is the power. And then from there, this is what I'm going to have. Note that when v is equal to 0, this term is going to vanish, and this is just going to be 1. That is just going to be 1, which is why we did not have to consider this in obtaining the Lamar equation. Now, the power emitted by the point charge at the retarded time is therefore given by this. Now we know, and then we write that and this, and when you rearrange this equation, this is what you are going to have. And when you write the value for dA is r squared sine theta d phi in r, therefore this is what you are going to have. And that integration there is difficult, and again we do not consider the complicated general case. Now in that case, but we consider the case where A and V are parallel or anti-parallel, where A and V are parallel and anti-parallel. Now where that are parallel to the other one, this term here, V cross A, is just going to be 0. The term that you are going to be left with is CR cross A. So as a result, this term here is given by this. Now we can go back and write this and plug it here in that equation here. But what is R dot U? The R dot U is nothing else but is just given by C minus V cos theta. Right. So assuming V is in along the Z direction, as a result, therefore this is just going to be given by this equation. The power radiated is just going to be given by this equation. Now the result for this integration, and of course we want to write this in terms of this, as you can see that this is just going to be a squared minus a squared cos squared theta. And if you use the fact that 1 is equals to sine squared theta plus cos squared theta, that equation there, it can be written as 1 minus that equation, the last equation here, it can be this one here. It can be written in terms of the a squared sine theta, so that this equation gives us this. Now the integration here will just be a little bit complicated, but I'm just going to give you the results for that integration. That integration has the value of this, where gamma is nothing else but is this. Now in that case, the power radiated is therefore given by this equation here. That is the power radiated, which increases rapidly as the speed of the charge approaches the speed of light. Now the general solution to the radiated power we do not derive is therefore the Lennard formula, which is just given by this. And what I want you to see here is if A and V are parallel or anti-parallel, therefore this term will just be equal to 0, and then the cross product is 0, and we get the results we derived, which is the maximum radiated power. Now if V are perpendicular to each other, therefore this is just going to be maximum. You are just going to have magnitude of V and magnitude of A squared. This is what you are going to have for that, which represent the minimum radiation for the given velocity and acceleration value. Good people, I would like to pause here, and good luck.